Hi, I'm Neel Phadnis. I'm the Director of Developer Ecosystem at Aerospike. Today, we're going to talk about multi-site clusters. So this is the overview of today's session. First, we'll look at what a multi-site cluster is and what it implies. Who needs it, or what application it enables. Then we'll explore a few key areas, such as how a multi-site cluster recovers from various failures. And this is going to be the thrust of today's session. We'll also look at the performance characteristics as well as why it is cost effective. Then we'll look at a couple of customer deployment examples in the payment processing area. And at the end, we'll have some time left for Q&A. What is a multi-site cluster? A cluster is a set of server nodes, and a multi-site cluster is a cluster whose nodes span multiple sites. So this is not to be confused with the setting where you have multiple clusters coordinated with the XDR protocol. XDR is the protocol that synchronizes data across multiple clusters. There are two key differences. One is a multi-site cluster is a single cluster, whereas in the XDR setting, you have multiple clusters involved. Second difference is a multi-site cluster has updates that are synchronized across all its replicas or all its sites, whereas XDR allows loose synchronization of data across multiple clusters. So what is a site? A site definition is pretty broad. A site can be a rack in a data center, or it can be an availability zone in a public cloud. And you can have combinations of these. So you can have a cluster, a multi-site cluster with two racks in the same data center or two racks in different data centers. Or you can have sites in multiple availability zones in same region or multiple regions in a public cloud. Or even you can have a combination of private cloud and public cloud sites, etc. So it gives you a lot of flexibility in deployment of a multi-site cluster. Not only that, but it also enables greater reliability with heterogeneous environment where the failure modes can be independent of each other. Another important aspect is that the sites can be geographically separated. And this is a relatively new configuration that Aerospike announced just last year in the Aerospike 5.0 database 5.0 announcement. And it enables certain business use cases that we'll look at briefly later. So apart from the just the term multi-site cluster, what it conveys, there are certain things that are implied when you say an Aerospike multi-site cluster. And one of them is it is an active-active. What we mean by active-active is the same data is concurrently accessible from multiple sites. And the benefit there is availability. You can access the same data across multiple sites at the same time. Also implied is the cluster is configured in strongly consistent configuration. So Aerospike allows both AP mode and SC mode. AP stands for available during partition. When the cluster partitions, it values availability more than consistency, whereas the strong consistent mode is exactly reverse. Strong consistency is always preserved, even during partitioning. And a multi-site cluster implies strong consistency. And the benefit of strong consistency for certain applications is they need the guarantee that the data is consistent across all its replicas. Another very important aspect of multi-site cluster is the data distribution is rack aware. And in this context, rack is equivalent to a site. So whenever we say rack, we mean it can be equated to a site. And what rack-aware data distribution does is it tries to have one replica on each site. So if you have replication factor of less than number of sites, obviously you cannot have a replica per site. But when you have a replication factor equal to number of sites, it provides exactly one replica per site. And this is very important thing because it enables two key benefits, two key properties of multi-site cluster. One is fast read performance. Because now that you have all the data accessible, available on each site, the reads can be local. And that means they can be very fast as opposed to having to go to another site, which could be geographically distant. And that makes a lot of difference in terms of read performance. Another benefit it accrues is even if you have a site failure, you have one or more copies of entire data across other sites. So there will be other sites that have the data available. So availability during site failure is another benefit that is derived from rack-aware data distribution. Another property or another recommended property of a multi-site cluster is they are symmetric. The sites are symmetric. So what that means is that each site has same number of nodes with similar capabilities. And the benefit that comes out of this is the performance and recovery characteristics of the sites are similar, which is a desirable thing. So as you can see, multi-site cluster not only is multiple sites, it doesn't not only spans multiple sites, but it also implies a lot of these desirable properties. And we'll see what applications these properties enable. So who needs a multi-site cluster, or what applications does a multi-site cluster enable? So applications needing global business transactions. And this trend is driven by mobile revolution, where all the users who are connected to their mobile devices, they can be connecting to the applications from anywhere in the world at any time. And the expectations are that the response from the applications will be fast. Whether you're sending money to your friend or you're checking on your e-commerce order, you want it to perform right away, quickly. Also, there's a trend of digital transformations within the enterprises, where not only are the businesses being connected to their partners and their customers, but also within the enterprise, things are becoming faster, always on, and so on. So as a result, things are getting more globally connected. They are always on and they are fast. And examples abound around us in various applications, supply chain, payment processing, shipment, and so on. And to enable this trend and such transactions, a data infrastructure, the database underneath all this has to be multi-site. It has to be close to your partners and customers. It needs to be consistent. You cannot rely on inconsistent, stale, or dirty data. It needs to be highly available, to be always on, and it needs to be efficient. When you purchase a database solution and when you operate it, it needs to be efficient. Now we'll look at some of the key areas of a multi-site cluster. And those are strong consistency, resiliency, performance, and cost effectiveness. So briefly touching on strong consistency has been supported in Aerospike clusters since 2018, when it was validated through Jepsen testing, which is considered a standard for consistency in distributed systems. So it's been there for a while, but briefly, the guarantees that Aerospike provides through its strong consistency is there are no lost data, there are no dirty reads, and there's no stale reads. And these are very important properties for business transactions. Next, we'll talk about resilience in greater detail. So not only Aerospike allows for planned outages where data remains available through rolling upgrades. So whether it's hardware maintenance or software upgrades, you would have all the data available through the rolling upgrade procedure. But also, when you have unplanned failures of various sorts, they could be node failures, connectivity failures, or site failures. How Aerospike clusters recover from that, we'll look into some of those situations in greater detail. But the key points to remember are the detection and recovery from failures is quick. And we'll see what enables that. What are the mechanisms that enable a quick recovery from failures? And while a partition is recovering from failure, it still remains available. And let's look into that a little more detail. So understanding cluster recovery requires, some understanding of some key concepts in Aerospike. So one of the things to remember is how data is distributed and replicated. So records are held in partitions. So you hash the key of record and it falls in one of the 4096 partitions that defines namespace. And each partition has replication factor number of replicas. And these replicas are distributed across the nodes of the cluster. The notion of succession list is essentially each partition has an ordered sequence of nodes in which its replicas get assigned. So the key point to remember is basically this list is deterministic. It's based on static factors like node ID and partition ID. So just by knowing which nodes are available in a cluster, you know where the replicas would be for a given partition. Another important notion is the roster, which is essentially simply all the nodes in a healthy cluster. So all the nodes in the cluster basically form the roster. Then how is the cluster membership at any given point determined? The heartbeats is the mechanism that the cluster nodes use to talk to each other and tell each other that they are alive. So they exchange these regular heartbeat messages with all other nodes, and there's a collective understanding of what nodes are part of the cluster at this moment. And the heartbeat messages are like sub-second frequency, and if you don't hear from a particular node for a certain number of heartbeats, it is considered unavailable or dead. And through this mechanism, a failure of a node or inaccessibility of a node is detected quickly, and a new cluster state is formed within seconds. Then there's a notion of replica migration. So when there is a failure, you walk through the succession list for a given partition, and the first available node is the master, and replication factor -1 subsequent available nodes are where the remaining replicas reside. So that's how you determine at any given cluster state where the replicas for given partitions are. And that's a static algorithm in the sense that independent of any information from other nodes, except that whether the node is alive or not, a given node can determine what data it owns as a master or as a replica. So when there's a failure and data is, master is migrating or the new replica is being created, the requests are still being proxied to the right node. So the partition remains available during that period. And that's a very important property. So even when you are creating multiple replicas, it is not because the current availability of the data, it is for the future potential failures. You want to ensure that you have enough redundancy to guard against the future failures. That's why you're replicating the nodes, but the data remains available for current requests. Now we'll quickly walk through a site failure or cluster split scenario and how a multi-site cluster recovers from it, and also introduce the new solution for Tiebreaker Node that we have introduced recently. So let's look at this scenario where you have a 3-site cluster with 9 nodes, 3 nodes per site with a replication factor of 3. And as you see in the diagram, we are looking at 2 partitions, green and yellow partitions for the sake of simplicity. And in this case, either site 1 fails, which is a site failure case, or site 2 and site 3 are unable to talk to site 1 because there's a network partition. Both of them result in 2 subclusters. And let's just take the example of cluster split for the rest of the discussion here. So the 2 subclusters will be, in the case of a partition scenario, site 1 being 1 and site 2 and site 3 being the other subcluster. The cluster split rules are applied, which say basically a partition in a given subcluster will be available if it has the majority of the nodes and at least 1 replica. So that's one case. And that case applies to the subcluster site 2 and site 3, because it has the majority of the nodes, 6 out of 9, and it has at least 1 replica for all the partitions. Actually, it has 2 replicas for all the partitions because of the rack-aware distribution, where each site has a replica of all the data. The second and third rule are not applicable here. The second rule applies only in a 2-site cluster, which has equal distribution of nodes. And the third one never applies to multi-site cluster because of the rack-aware data distribution, because no site can have all replicas of the partition. So once the subclusters are decided and formed, basically a new cluster is formed with site 2 and site 3, then you need to assert the one master rule. So any master partitions that were in site 1, that ownership is transferred to appropriate replicas in site 2 and site 3. And for all the copies or replicas that are in site 1, new replicas are created to maintain the RF replica rule. So with that, the new clusters formed, and while the data migration is happening, all the partitions are still available for any incoming requests. So at this point, let's look at the new feature that was introduced, which is called a tiebreaker node. The problem is, as I alluded to earlier, site failure recovery in a two-site cluster is not automatic. So in case of a non-majority subcluster, so one site fails, the other site in a two-site cluster, it could be a minority node, minority site, or it could be equally split site where the distribution of nodes is equal. In that case, since there is no majority of nodes, it cannot own all the partitions, and it basically the data is not available essentially, effectively. This situation doesn't arise in a three-site cluster, as we saw earlier. One site failed, and other two sites took over without any hassle, without any intervention, manual intervention. But the three-site cluster has a greater cost of both just operationally as well as hardware-wise. So the solution here is introduce a tiebreaker node, where you deploy a tiebreaker node at a third site, and it remains in a quiesced state, which means that it is part of the cluster, but it has no data. It participates in majority, minority voting to figure out which cluster form, which subcluster forms, but it doesn't own any data. Its sole purpose is, as I said earlier, is to provide the majority when a non-majority site remains, so that the non-majority site can remain available without manual intervention. So that is a new feature. Essentially, it's a 2.5 site cluster, if you will. It gives you the benefit of two-node cluster cost at a two-site cluster cost at a three-site cluster reliability, if you will. Now, let's look at the performance characteristics of a multi-site cluster. So assuming that a round-trip latency in a multi-site cluster is R, so from a site-to-site round trip is R. Let's first look at write, because it's relatively simpler. So as you remember, it's a strong, consistent setting in a multi-site cluster, and all replicas are written synchronously. So whenever you do a write, the master coordinates with the rest of the replicas and returns the result when all the sites are updated, all the replicas are updated. And so depending on whether the master is local or remote, it would take R or 2R latency. So that is the write performance, and depending on how farther apart your sites are, and as you can so the multi-site cluster is a pretty general architecture. You could have sites that are not very far apart, within a few miles of each other potentially, or thousands of miles, or even across the continents. So depending on the separation, your write performance will vary. In the case of read, the latency depends on the read consistency level you choose. And Aerospike provides multiple read consistency levels in the call, in the function call, API call that you make. So you can specify a read to be linearizable. So in the order of most to less stringent, the most stringent consistency level for read is linearizable, and which basically guarantees that the read is consistent across all the clients that are running against the cluster. In this case, all replicas are checked, and therefore it goes, first this goes to master, and master does the replica check. And depending on where the master is, just like write, as we discussed earlier, depending on where the master is, it can take hour or 2 hour latency for a linearizable write. The next level of read consistency is session, and that guarantees consistency within the session. So you're guaranteed that your reads within a session will not be stale. So that read has to be done from a master. There's no replica coordination required for session consistent read, and therefore, depending on where the master is, you just need just one round trip interaction, which means if the master is local, it's very fast, millisecond range. If it's remote, it takes one round trip across the site. The third level of read consistency is allow replica, practically as good as session. And however, the reads happen from the local copy, which means your performance is much faster, about a millisecond range. The recommendation especially for geographically separated clusters, the separation is to follow allow replica consistency. It is much better for performance, and especially in a cloud environment, public cloud environment, where you get charged for egress from the cloud. This works out much better cost-wise as well. So next thing is the total cost of ownership that Aerospike provides is low, and it stems from multiple factors. First of all, various innovations that have gone into the Aerospike over the last decade or so, including hybrid memory architecture, which essentially improves the density of how much fast storage you have available by combining SSDs with DRAM. That's the hybrid memory. And SSDs essentially give you a lot denser, high-speed storage at a much cheaper cost. Other innovations include automatic data distribution and smart client, which make essentially the application and failure recovery, those aspects are taken care of, and your application development and resiliency becomes much better. The second factor is Aerospike solution has been around. The cluster solution has been around for almost a decade, and it has been deployed with large mission-critical deployments. And some of our customers have reported multi-year uptimes. So even if they had to do hardware maintenance and software upgrades, with the rolling upgrades, they were able to keep the data available. A higher data density per node, which results in smaller cluster size. And that is, it directly results in a smaller hardware cost, but also operational costs of, keeping the cluster running. Also, as we saw earlier, because the reads can be local, you don't incur the cloud egress charges if you have deployed this in a cloud environment. And in general, because of the reliable cluster solution that Aerospike has, the maintenance costs are low. So all of this results in low total cost of ownership. At this point, we will switch the gear and briefly look at a couple of customer examples. Both of the examples come from the payment processing space. The first example is the European Central Bank. They have this TIPS system, which is essentially consumer-to-consumer payment, which happens through their respective banks, because two consumers, the payer and payee, may not be members of the same bank, that it needs an intermediary to facilitate that transaction, and ECB is that mediator. So they have hundreds of member banks through which these transactions flow. The requirements include, very fast, end-to-end transaction within seconds, very low cost. So the members are charged for this service, and it had to be a fraction of a euro cent. And the throughput in the system, this was several years ago, thousands of payments per second. And these are end-to-end transactions, which result in multiple reads and writes within Aerospike. So the actual throughput at the Aerospike system level is much greater than that. And of course, the system has to be always available. So this solution has been in place since 2018. So we are at the end of the presentation, and I will summarize the key points, which are Aerospike Multi-Site Cluster provides active-active operation across multiple sites. It delivers strong consistency and always on availability at a low cost. And all of these attributes of Aerospike Multi-Site Cluster makes it a great fit for global business transactions. And we have multiple customers that are successfully running mission-critical payment processing at scale with multi-site clusters. So here are some of the resources that you can check out. There are multiple blog posts that directly talk to the material in greater detail from this session. And there is the Aerospike Developer Hub, which has all kinds of good stuff that you might want to look at to check that out. And thank you very much for attending this session. And I will open up the floor for any questions that you might have. Okay, so we are in the Q&A segment now, and I see a couple of questions. I know we are slightly over time, but I think we can handle a couple of questions. Shouldn't take more than a few minutes. So first question, without further ado, is when should one consider a multi-site cluster over multiple clusters linked with XDR for specific application needs? So I think, when should one consider, both are multiple site deployments. What are the differences? How should one look at a multi-site cluster versus multiple clusters linked with XDR? And the simple answer to that is, strong consistency. If your application needs strong consistency, then you need a multi-site cluster which is configured with SC, which is strong consistency, which means that all replicas are always kept consistent. When you have the situation where multiple clusters are linked to XDR, it provides loose synchronization, but there's no guarantee that the replicas across multiple clusters will be consistent. And when you try to sort of merge the forked data, multiple versions, there is no guarantee that the data won't be lost. So, so there is there's that clear distinction. Strong consistency is the distinction. Not to say that XDR has its advantages that potentially a multi-site cluster may not have. And some of those are, for example, it's typically fairly common and easier to set up XDR configuration for disaster recovery. And if you have data locality regulations, such as GDPR, XDR allows you finer granular control over replication. And if your application needs really fast local write performance, then you can get that with multiple clusters as opposed to a single cluster spanning multiple sites. And also generally at the XDR, multiple clusters affords you greater site autonomy for each cluster. So it depends on your application needs, but also an important thing to note is they are not mutually exclusive. So you can have both a multi-site cluster as well as clusters spanning multiple sites, which are coordinated with XDR. You can deploy both to meet your overall data and application objectives. So another question is, what are the design considerations in deploying a multi-site cluster in a public cloud environment? So a public cloud environment has huge benefits in terms of its flexibility, its elasticity, pay-as-you-go model, and so on. But you have less direct control over resources as you might have in a data center environment. So the delays, the variations, and failure modes can be significantly different. And those must be considered for your applications: latency, throughput, reliability, consistency, and so on, all the requirements. And not all those requirements, there are trade-offs to be made. So from a multi-site cluster perspective, the key things to think about are adequate bandwidth between sites. That's important because the whole cluster fabric and heartbeats, that requires constant communication among sites, and the key things that you would adjust or configure are the heartbeat frequency and the number of missed heartbeats that is construed as a node failure. And also one thing to also remember is you should configure your reads to be local with allow replica consistency level, so that you save in a public cloud environment. If there's an inter-region data transfer cost, you'll save on those. But in general, I think it's good to consult with experts such as Aerospike SAs and review your design and data, both of data distribution as well as application, to meet your goals. And an easy way is to essentially use Aerospike's cloud managed service, because that essentially provides you a kind of package solution right from it covers the entire gamut from design and planning all the way to deployment and management. So those are some of the considerations for public cloud environment. And maybe I guess there's one quick question that I'll answer and then we'll stop. What kind of latencies are expected in a geographically separated multi-site cluster? So we did some experiments across East and West regions in a public cloud environment, and we observed about the round trip time of 70 milliseconds. So the writes were clustered around 70 and 140 milliseconds. And there's a good blog post that's available. I listed that in my slide deck, so you can look at it for greater details. And reads can be kept local, as we said multiple times, by choosing allow replica. And so those are the kind of performance numbers. And there are some tweaks that you can make for round trip the ping time, the round trip delay among sites, and that's one configuration parameter apart from heartbeat, etc. But in general, getting data and application design reviewed by SAs, our system architects, and because there are these factors are sometimes opposing to each other. There's trade-offs to be made. So data size, distance, throughput, performance, cost, etc. have to be considered, so you can have the right balance and right trade-offs can be made. So that is kind of a gist of how you what kind of latency you can expect in a multi-site cluster environment. So I think we are over time, so I would like to wrap up and thank you for attending this session, and hope you have great time in the rest of the summit. Thank you.